With exponential equations, the really important thing to remember is the equate the base technique. So remember that if we've got the same base, then x and y will be the same. Now, some students do this as well. So if we've got 2 to the x equals 2 to the, say, 3 plus 1, what they say is, well, we've got the same base here, so x is equal to 3. Not the case. Okay, so that one there, you can't use that. The bases are not equated. Now, alternatively, if it was 2 to the x equals 2 to the 3, and we had 1 on either side, so plus 1 and plus 1, then because they're in the exact same format, then we can again equate the bases, but it's got to look exactly the same on the left and the right to use this technique. There's all of these other index laws, so I won't go through each one and explain it. You'll just need to apply it to these scenarios. Right, so this one here, we're going to use the power to power rule first of all, so equals 3 brackets. Now, 2 to the 4 is equal to 16, x to the 8, y to the 12, all over that 2 to the y to the 2, 3 times 16, actually let's just cancel that now while we can. 3 times 8 is 24, x to the 5, y to the 10. Right, this one here, what we're going to do is, if we've got that divided by that, let's just put one on top of the other. So 15 x to the 5. Let's just use the power to power rule straight away. So this is 5 to the x to the 5 to the 4, which is x to the 20, y to the negative 8, all over, didn't need the brackets there now, but doesn't matter, 3 x to the negative 8, y to the negative 2. Okay, so that's going to be 5x to the 28, y to the negative 6, and probably appropriate. It doesn't say to write your indices as only positives, but I would. Okay, next one. Let's go with this one here. So 5 to the x equals 125. Okay, so what we want to do is equate the bases. So this is 5 to the, and that I just know from experience is 5 to the 3. Okay, but you got to remember that this is going to be equate the bases unless it's a calculator question. So invariably, you will be able to reduce these numbers down. So it's about just playing with the numbers. Right, so I've got the bases the same, so I'm going to equate them. So x is equal to 3. Right, so this one here, what I'm going to do is say that this is 1 over 5 to the x equals 1 over. Now, this is going to be 5 to the 4 because I know that 125 multiplied by 5 is 625. All right, so now that I've got it in this form here, they're the same, they're the same, that's the same, that's the same, so I can equate them. X is equal to 4. All right, this one here, what we're going to do to this one here is try to reduce these down to a base 2. So this is 2n times 2 to the 3, and we're raising that. So 8 is 2 to the 3. We're raising that to 4n to the negative 1 equals 2 to the 5. Okay, this is 2 to the n times 2 to the 12n take 3. So make sure that when we multiply these two together that you imagine that in a set of brackets and then distribute the 3 across the terms equals 2 to the 5. Okay, so common bases, what we do is we add the powers. So I've got 2 to the 13n take 3 equals 2 to the 5. Now the bases can be equated. So what we can do is say that 2 equals 2, so 13n take 3 equals 5. 13n equals 8, n equals 8 on 13. Yeah. All right, last one here. Solve the following for x, common question in exams. Okay, so the technique we're going to use on this one here is I'm going to rewrite this as 3 to the x all squared, take away 2 lots of 3 to the x, take away 3 equals 0. Then I'm going to say let a equal 3 to the x. Have a look at what cool thing happens now. A squared take away 2a take 3 equals 0. So this is what I refer to as the hidden quadratic. All right, so let's try to factorize this. So we've got 3, 1, a, and negative, a take 3, a plus 1 equals 0, a equals 3, a equals negative 1. Okay, but now what we've got to do is resubstitute our values back in. So I'm going to say, or continue this over here and say that 3 to the x, so I'm going to sub a for 3 to the x again, is equal to 3, and that can be written as 3 to the 1. Therefore, x is equal to 1. All right, 3 to the x equals negative 1. All right, now, if you think about this, all right, 3 to the x is a function that looks like that. And we're saying when is its y value going to equal negative 1, which is down here. And if you answered or you're thinking it's never going to equal negative 1, then you're right. It's never going to equal negative 1. So this is a solution we're going to avoid. We're going to say 3 to the x does not equal negative 1 as 3 to the x is greater than 0. Okay, so the only solution we get is x is equal to 1. All right, on to logarithms. Love logarithms. So does Hannah Fry. So check out her video on logarithms. She does a fantastic example of logarithms in handling weights, and also talks about the criminal justice system of all things. So very interesting to think about the applications of logs. Now girls, this should not be any revelation. 2 to the 3 equals 8. But there's an alternate form of writing this. We can actually say this, log 2, and probably good idea to get in the practice of writing brackets there, log 2, 8 is equal to 3, okay? Now, you need to be able to understand what this means. So the left side can be read as the question. So I see this as a question. So in fact, I shouldn't say log 2, 8, I should say log 2, 8, implying that there needs to be an answer to that. And basically what it's saying is, hey, if you've got this base 2 here and you want it to raise it to a power to equal this thing here, to equal 8, what would the power be? And the answer is 3. So the left side can be read as what power would 2 be raised to so that it is equal to 8? And the answer, or it equals 3. So let's have a think about this one. This one here is a question. So log 2, 1000. That says 10 raised to what number will equal 1000? So 10 to the power of what equals 1000? So 10 times 10 times 10 is equal to 1000. So it would be raised to the power of 3. 10 raised to the power of 3 equals 1000. So what did you say to yourself when you evaluated this? I would say 10 raised to what power is equal to 1000? 10 raised to what power would have it equal to 1000? The answer is 3. Okay, so inverse functions. Just remember that for an inverse function to exist, the original had to be a 1-to-1. But remember that if I've got a parabola and I inverse it, it's going to look like that. And what the result is not a function. Okay, it's a relation but not a function. So we need to just restrict those domains. Now it's convenient with exponentials and logarithms because an exponential function is 1-to-1. Okay. For inverse functions, if the original function is 1-to-1 or has been restricted, are reflections of each other in the line y equals x. Again, just recall that that line y equals x is the reflection point for an inverse function. So here's a function here, f of x equals a to the x, and we want to find its inverse. All right, so we're going to say let y equal f of x equals a to the x. And for the inverse, what we're going to do is swap x and y. So we're going to say x is equal to a to the 6, no, a to the y. All right, now what I need to do is get it into the form y equals, but there's a problem. This is in the exponent, okay? So what I want to do is bust it out of the exponent, and the method we're going to use is to convert it into log form. All right, so we're going to say that this can also be written equally correctly as log a. All right, now what I'm doing is I'm using the base, so the base to the base, okay? So log a. Our number's going to be x that we're logging, okay, and the answer is y. And this basically says a raised to the y will give us x, all right? And so a good thing to do, so that's its inverse, okay, so we're going to note that. But a good thing to do and a good thing to practice your conversions is to then take the logarithm and convert it back to exponential form, okay, which is a to the y equals x. And then take that or hide that and see if you can convert that into log. Log a x equals y. Okay, so practice that move over and over again. It's an important one. Okay, so what I'm going to note here is that the domain of the exponential function is going to be all real numbers, and the range of the exponential function, the original function, so domain of f is all reals, the range of f is going to be 0 to infinity. Call that a to the x's or whatever base you've got look like that. Okay, so remember what happens when we inverse functions is the range becomes the domain. So I'm going to say that f negative 1, so f negative 1 is a function such that it has a domain of 0 to infinity, mapping to the codomain, which is a set of all real numbers, where f negative 1 of x is equal to log a x. There we go. So that's written in full function notation. So the graphs of y equals a to the x and y equals log a to the x are actually inverse functions. So that a to the x and that are inverses of each other. So if this is our exponential function here, this will be our logarithmic function here. Okay, that's an inverse. All right, if this is our exponential function here, a to the x, with a reflection in the y-axis, then this is what our logarithm function is going to look like. And that's really important to know that if you know what the exponential function looks like, it can help give you an idea of what the log's going to look like. Okay, two common bases for logarithms are base e and base 10. Base e is the natural logarithm, can be written as log ex or ln x. I've heard examiners say that you should use a ladder or suggest that you use it, but girls, I'm afraid I can't do it. Now, what you've got to make sure you do is subscript that e, and I would strongly advise you to bracket the x. The common logarithm is of base 10, can be written as log 10x, but if it's written like this, the base 10 is implied. But again, I always write the base, so there's no kind of like, ooh, I wonder what base he's talking about here. But that, if it's written like that, you're not like, oh, what's that, Mr. Miller? Base 5, base 6, base 15.5? No, this is base 10, okay, it's implied. When you write the base of a logarithm, you need to make it clearly subscript. This seems to be a pet peeve of one examiner who has mentioned this thing here. I've talked about it to you. He calls this loge, okay, loge. So in every instance I've heard him speak. So you don't want to be losing a mark for loge. So let's just make sure that if you are going to use it, you subscript it or you use lnx. Found that one student last year in my class used lnx. The rest of the students used log ex, use that notation. So there's a bunch of laws that govern logarithms. So recall that if I've got log AMN, then I can break that open by writing it as log AM plus log AN. It's division. I can bust that open using a subtraction. This one here is an important one. If this number being logged is raised to a power, I can grab that power and slot it into the front. Okay. All right. So another cool thing here is if I've got 1 on m, if I'm logging 1 on m, that's m to the negative 1, and I can grab that power, slot it out the front, and that means it's just negative log a of m. Logarithm of 0 and 1, the log a of 1 is equal to 0. Think about it. A raised to what number would give us 1? That's the law. Anything raised to the power of 0 is 1. Right, this one here says a raised to what number would return itself? Okay, and that's going to be raised to the power of 1. Okay, so important to know that they are rules. All right, other things to note. Log ax squared and log ax squared, notice the position of the brackets, they're not the same. Log ax squared is equal to log ax times x, and log ax squared, this version of it, is actually should be said as log ax all squared. Okay, so it's log ax all squared is, what have I written there, is equal to, so I've forgotten some equal signs there. Log AX times log AX, completely different to what that says. This one here is really important. Okay, A log AB is equal to B. So these basically just cancel each other out. And the way I think about it is if I've got 5 log 5, 25, then what's log 5, 25? That's 5. 5 raised to what number will give me 25? The answer is 2. 5 squared is equal to 25. So what happens is this 5 log 5 thing kind of undoes itself, okay, leaving us with just this thing here, okay? And it doesn't say stranded in midair. What that does is it undoes itself, meaning the answer is 5. Or the opposite of log AX, okay? So x goes to the front, so x log a means that a raised to what number will give a, that's x times 1 or equals x. Again, it's really important to know why that's a rule. Right, so let's evaluate a couple of logs. All right, evaluate log 464. 4 raised to what number will give me 64? The answer is 3. All right, over here, we've got solve the following for x. 3 raised to what number gives me x take 1? The answer is 4. 3 raised to the 4 gives me x take 1. Now 3 to the 4 is 3 times 3, which is 9, 27. 27 times 4, mental blank here, I think it's 81. 7 4s are 28. Oh my goodness, what am I doing here? 27 times 3, you goose. 7 3s are 21, 2 3s are 8, 81, as I thought, equals x take 1, x is equal to 82. Okay, so notice to solve these, what I do is I actually bust them into exponential form to solve. So this one here is x to the 3 on 2 equals 27. All right. How are we going to do this one here? Well, what I'm going to do is raise this to the 2 on 3 and raise this to the 2 on 3. So do the same thing to the left and the right. All right, so that will give me 6 on 6, okay, when I multiply those out, which is equal to 1. And all I'm going to do for this one here is say that this is 27 to the 1/3 all to the 2. So that's going to be x is equal to, now that's the third root of 27, which is 3 squared. X is equal to 9. Is there another way that we can do that one? Yeah. All right, solve 2 to the x equals 6 using the identity using base 2 log or base 10 log and then simplifying. Okay, I'm not really sure what the identity is, but let's just go ahead and do it. So all I need to do is solve for x. So I'm going to say, I'm going to convert to log form. So log 2, 6 is equal to x. Okay, so all I've done is I've switched that to log form. So the answer is x is equal to log 2, 6. Right, using a base 2 log. Well, what I'm going to do is take the log 2 of both sides. I'm going to go log 2 to the x equals log 2, 6. All right, and then what I'm going to do is use that rule. So that index goes out the front. Log 2, 2 equals log 2, 6. Now log 2, 2 is equal to 1, so that's x is equal to log 2, 6. There we go, got the same answer. Or base 10 log. So let's take the base 10 log of both sides. So log 10, 2 to the x equals log 10, 6. X log 10, 2 equals log 10, 6. X is equal to log 10, 6 over log 10, 2. Okay, don't think I can do anything else with that. So there are 3 different variations of how to solve this one. This one with a base 10, this one converting to log form straight away, this one using that log 2, 2 rule, which equals 1. Okay, so believe it or not, that number there is exactly the same as that number there, and it's worth just pursuing this because you'll sometimes get a different answer and think that you're wrong. So I want to show you that like you are right. So let's go over to the calc and find our logs. Now here is our log 10, okay? So we're going to go log 10, 6 over log 10, 2. Let's just get an approximation on that, 2.58. So if this is correct, what should happen is if I take we'll do the log 2, 6 and approximate that, it should be exactly the same number, okay? Because I've done what is a completely allowable move. Bang, same number, okay? So important to note that those are exactly the same thing. So sometimes you will need to carefully check your answers to make sure that you are indeed correct. All right, what are the coordinates of the x-intercept of f of x equals this? So it's an exponential function, y equals -2. I'm going to go through there. So we're looking for this coordinate here. So when do the x coordinates happen? It's when y is equal to 0. So we're going to go 0 equals e to the x plus 1, take 2. All right, I'm going to add 2 to both sides, e to the x plus 1. And what I need to do to solve for x is I need to bust it out of the exponent. And the method or the answer to this is, let's convert to log form. So log e 2 equals x plus 1, x equals log e 2 take 1. So the coordinates of the x-intercept are the very attractive log e2 take 1, comma 0. Explain why we can't find the x-intercept of this. That's why. Doesn't. But, I don't know, to hell with that. Let's find it. Okay, it's the kind of crazy cat you're dealing with here. E to the x take 2 plus 3. -3 equals e to the x take 2. Oh, what's wrong with this? Log e -3 equals x take 2. X is equal to log e -3 plus 2. We've got it. The coordinates are log e -3 plus 2 comma 0. So Broken question? No, that's a correct question. It doesn't have an x-intercept. Why did we find one? Well, we didn't. This does not exist. E raised to what power will give me -3? E raised to what number will equal -3? Well, this is like e to the x equals -3. When is this function going to be negative? Well, it's never going to be because e to the x looks like that. So the problem here is e to the x is always greater than 0, or we're going to say that log e -3 does not exist. Okay, and the rule is that you can't log a negative number. Okay. Okay, so some practice here. This one was done poorly on a 1-2 methods a few years ago. Solve the following for x. Okay, so note here what we've got here is log 4 on the same sides. So we can simply equate these two. So 15 take x squared equals x squared take x. And what we're going to do is let the right hand side equal 0. We've got 2x squared take x take 15. X, 2x, what's that going to be? Like 3, 6. Yeah, I think that's it. 6 is negative, 5 is positive. 0 equals x take 3, 2x plus 5. And then x is equal to 3, x is equal to -5 on 2. Now, very important, girls, that with quadratics, they're the solutions. But this quadratic is a means to an end to solve this particular problem here. What we've got to note here is that in each case, we've got to test both our solutions. Okay, so if I jam 3 into this, okay, what's going to happen is I'm going to get 15 take away 9. That's the log of a positive number. And here I'm going to get 9 take away 3. That's legit. Okay, that will give us a solution. All right, what about -5 on 2? Okay, so -5 on 2 when squared is 25 on 4, which is equal to 6 1/4. So that's cool as well. 5 take away 6 1/4, that works. All right, let's look at this one here. We've got 5 on 2 squared is 25 on 4, and we're removing from that negative, well, it's negative, so it's going to be plus it. So that's going to be positive as well. So both of the solutions are perfectly appropriate in this case. All right, this one here, remember this one from a test a few years ago. Student said the answer was 4. No way. Okay, so this one here, what we're going to do is go log 5, and we're going to rewrite this as 2 to the 3 over log 5, 2. We're going to use that rule to slam that out the front as the coefficient for the log. Cancel them off, answer's 3. All right, this one here, we're going to go log 7, 7 to the -1. Use that rule, -1, log 7, 7. And log 7, 7, 7 raised to what power will equal 7? The answer is 1. This is just -1 as an answer. Okay, this one here, solve the following for x. Okay, so to do this one here, what we're going to do is rewrite this as log e x squared plus log e 4 equals log e 9x take 2. All right, so now what we're going to do is use that log law to combine. Okay, so same bases for the logs. So when we've got common base logs being added, let's go and have a look at our laws. Common base laws being added, what we can do is multiply. Okay, so what we've got here is log e 4x squared equals log E 9x take 2. All right, so because we've got the same kind of template here on either side, we're going to say that 4x squared equals 9x take 2. Now we're going to say 4x squared take 9x take plus 2 rather is equal to 0. So let the right hand side equal 0. And let's proceed with a solve on this one. So we've got don't tell me I got it first time, did I? I think I did. 4x take 1, x take 2 equals 0. X is equal to a quarter, x is equal to 2. All right, and again, really important that we test these solutions. So this one here is going to be a quarter, can log that. That we don't worry about. This one here is going to be 9 lots of a quarter is 9 on 4 equals 9 on 4. What was I doing here? 9 times a quarter is 9 on 4. Take away 2. So what have we got? 9 on 4 is 2 and a quarter. Take away 2. Yep, that's all good. 18. Yep, so both of those solutions are appropriate. All right, the last one is this one here. Okay, for this last problem, what we're going to do is attempt to solve on this. Now, here's the way I'm going to do this. I'm going to say that this is log E, and I'm going to multiply these two together. So that's 6x plus 10 equals log E to the 2. Should I do that? No, I'm not going to do that. No, forget that. Instead of that, I'm going to leave it as 2. All right, now what I'm going to do is say e to the 2 equals 6x plus 10. So I'm just going to drop that into exponential form. Now what I'm going to do is go e to the 2 take 10 equals 6x. X is equal to e to the 2 take 10 over 6. Okay, one last thing for your notes as well, girls. So if I have this problem here, log, what are we doing? Log 10, 0.1. Okay, so say I've got that problem there. Now, if I asked you, is this here greater than 0 or less than 0, you'd probably say that the answer is greater than 0 because, well, there's no negative sign out the front here. But in fact, let's tell you something, this is actually a negative number right here. Now, how do we know? Well, log 10, that can be written as 1 on 10. Log 10, 10 to the negative 1. So I'm just rewriting these using my log laws here. Negative 1 times log 10, 10. Log 10, 10 is just 1. That's negative 1 times 1. That equals negative 1. So this is actually log 10, 0.1 is actually a fancy way of writing the number negative 1. So pop that in your notes, girls, and just note that from here in, it's very difficult to tell with log. So it's not very difficult, but it's sometimes challenging to know whether a log value is either negative or positive because it doesn't have a negative or positive sign out the front. We're used to that. We're used to seeing negatives and positives, but in this case, it's just not there. So we need to know something about the manipulation of the numbers to work out whether it's negative or positive.